Lesson 6, a special point. I don't only have a point to make with this lesson, I have a special point to make for this one. Today we're going to be looking at salt piles. Yes, piles of salt on top of triangles. Let's take a look. First, I want you to watch this clip of someone pouring salt over a cutout of a triangle and just observe how the salt is piling up. Take a look. Fascinating. So the question that I want to bring your attention to is, why did the salt pile up and make those ridges and that peak? Now this is actually an experiment that you can do at home. Just ask your parents to cut out a triangle from some cardboard and pour some salt over it into a bowl. And you should get something that looks just like this, where these ridges and this peak kind of forms no matter what the triangle actually looks like. Cut out the triangle any way you'd like, and you'll see something similar happening there. So to help us figure out what's really happening here, we're going to be taking a look at angle bisectors. 6.2, point and angle. Here's angle BAC with two different sets of markings. We're going to be making some observations about these two shapes. In the first one, point E, we're given the fact that it is the same distance away from rays AB and rays AC. Now it looks to me that EA would also bisect angle BAC. And the second figure looks like point H is bisecting angle BAC, and I believe that H is the same distance away from both AB and AC. Now let's try and prove that those two things are true. First up, we're going to prove that angle EAC is congruent to angle EAB. That's right, we're doing our classic two-column proof here. First thing, I'm going to want to label these points because we're going to need to talk about these two triangles. So I'm going to label F and G. And first thing we're going to say is that EF is congruent to EG because that's something that we are given. We also know that EA is congruent to EA because it's the same segment. We call that the reflexive property. Then finally, I can also say that GA is congruent to FA. Now the reasoning here, I'm kind of taking a bit of a jump in the logic, and that's because I know for a fact that they're both right triangles. And for right triangles, we know Pythagorean theorem must be true. A squared plus b squared equals c squared. So if two of the sides of a right triangle are the same, then the third side must also be the same. And that's what allows us to say that GA is equal to FA. Which means that all three sides of our triangles are congruent. So we can say that they're congruent based on the side-side-side congruence theorem. Now that I know that triangles are congruent, I can say that angle EAC is equal to angle EAB because of CPCTC. Next up, prove that HG is congruent to HF. So now we are looking at the same figure, but the given information is different this time. This time, we're given the fact that angle HAC is equal to angle HAB. That's the given information. Now I'm also going to use the fact that angle HGA and angle HFA are both right angles, which we're also given. So therefore, they must be congruent to each other as well. We also know that HA is congruent to itself by the reflexive property, which means that once again, these triangles are congruent because I have an angle, and a side that make them congruent. Angle, angle, side, congruence theorem. Which then means I can prove what I was trying to prove, that HG and HF must be congruent to each other because of So, what did we just prove? We just showed that basically given the same diagram, that if a point is the same distance away from two rays that make up an angle, then that point must lie on the angle bisector. And in the second diagram, we showed that if a point is on the angle bisector, then it must be the same distance away from the two rays of the angle. So this is one of those statements where we had to prove the same exact statement but in different directions. If we know it's the same distance away, it's on the angle bisector. If it's on the angle bisector, we know it's the same distance away. Both of those things have to be true at the same time. Now, how does this relate back to our salt piles? Well, if you take a look back at these pictures, you can see that these ridges that are forming on these salt piles are forming the angle bisectors of this triangle. And it makes sense when you think about it, because when you pour the salt over the triangle, the closer it is to the edge, the more it's just going to fall off the side. But the further away it is from the edge, or the furthest away it can be from both edges, is where the salt is going to be able to pile up the highest. And that's where we're seeing these ridges form. And we can see these ridges actually form the perfect angle bisectors on these triangles. 6.3, what if there are three sides? So here we're given triangle ABC, and we have two of the angle bisectors already drawn in. They intersect at point G. So first thing we're asked to do is fill in the distance from point G to the sides of the triangle. Now remember, anytime you have distance from a point to a line, it's always the distance that is perpendicular to that line. So it should look something like this, with those dotted lines showing the distance from the point to the side. Now we know since G is on the angle bisector of ABC, we know that it's the same distance away. I should say, we know that point G is the same distance away from side AB and side BC. We also know that since G is on the angle bisector of angle ACB, that it's also the same distance away from sides AC and BC. So if it's the same distance away from AB, it's the same distance away from BC, and the same distance away from AC. Therefore, it's the same distance away from all three sides of the triangle. And therefore, if we were to draw in the angle bisector of angle BAC, it would also be on the angle bisector of angle BAC. So this point is another special point. It's what the lesson is named after. We call this the in-center of the triangle. It is the intersection point of all three angle bisectors of the triangle. And once again, if we look back at our salt piles, we can see that that is where the peak of the salt pile has to be. The highest point that the salt will be able to pile up is the point that is furthest away from all of the sides that it could fall down. So the highest point of the salt pile is called the in-center of that triangle. Now, the next lesson, lesson 7, talks about making a circle that is inscribed inside of a triangle. We're just going to talk about that right here and now. Something that would look like this. This is an inscribed circle inside the triangle. We would make that by doing exactly what we've been doing here, with just one more step of drawing the circle. So for example, in this picture, we know that G is the same distance away from all three sides of the triangle. So if I make G the center of my circle, and then I use the distance from G to one of the sides as the radius of my circle, then I would be able to construct what we call the in-circle to the triangle. And that's really all lesson 7 has to say. So I figured I would put it in here at the end of this video so we can just tie that whole thing in. So I also want to show you a small video of what it would be like to construct the in-circle from beginning to end. Here's what that would look like. preparing for this video, I watched that clip a number of times. So as I was going through, I was trying to speed it up on my own. And apparently the program I used does not like when you try and speed it up really quickly. This is kind of what happened. Take a look. Yeah, so that was interesting. And that's it.